Alright, so today we are going to work on some problems that I think are very interesting, where we're given a function, we have to prove that it's between certain boundaries. So in this case, we have f of x is equal to x squared minus 5, and we have to prove that it's between 2 and 3. So how do we do that? Well, for starters, we can actually set x squared minus 5 equal to 0. We can do that because it's a function. We're trying to find the solution where it is x equals 0, or y equals 0. And so we can solve this now pretty easily. We just add 5 on both sides. That's equal to x squared. And then the square root of 5 is equal to x. Now, we're only going to focus on the positive square root of 5. I know that if I can take the negative square root of 5 and then square that, that'll also give me 5. But in this case, we're only proving that it's between 2 and 3, so it doesn't really matter. The negative solution doesn't really matter. So we're just going to focus on the positive solution, okay? And now we have to prove that that is between 2 and 3. So I'm going to rewrite it here. Okay, how can we compare square root of 5 with 2 and 3? Well, we can't reduce square root of 5. It's not a whole number. But we can like unsimplify 2 and 3 into radical form. Well, 2 in radical form is just the square root of 4. And again, we're only focusing on the positive version. Square root of 4 is 2. That's all it is, okay? And then we have our square root of 5 here. And then 3 can be rewritten as square root of 9, okay? And so from this, we can now more easily compare all of these three numbers, okay? If you need to look at it in a better way, you can square these, but you don't need to square these if you don't have to, but you can square all of them, and then you can see that it's very obvious now. 5 is between 4 and 9, so square root of 5 is between square root of 4 and square root of 9. So our solution is between 2 and 3. So we proved that. It's great. This is a similar situation, because that was a lot, but now we can use what we learned to be able to do this in a slightly different way as well. So x cubed is equal to 2. And we have to prove that the solution is between 1 and 2, okay? So let me just rewrite it here. X cubed is equal to 2, and therefore x is equal to 2 to the 1/3 power. And I'm writing it like that, and you'll see why, but it's important sometimes to write things in certain ways when there are multiple notations, but I'm just going to write it like this, okay? From this, we have to plug it back in here, but you can see that it's going to be less than 2, because anything to a 1 over x power is going to be less than your original number. For example, 4 to the 1/2 power is just for the square root of 4, which is 2. And so you can see 2 is less than 4. Same thing with your 1/3 power. 8 to the 1/3 is 2, okay? And 2 to the 1/3 is going to be less than 2. So you can already tell that 2 to the 1/3 power is less than 2, or 2 to the 1st power. Now, how can we rewrite 1? Well, 1 is just 2 to the 0 power, because anything to the 0 power is going to be 1. So this is just 2 to the 0 power, and that you can tell it's going to be less than 2 to the 1/3. And now we can compare all of these. You can see right here that 2 to the 1/3 is between 2 to the 0 and 2 to the 1. But you can also take the log base 2 of both sides, and then you get 0, 1/3, and 1. And you can compare the exponents this way, and you can see that 1/3 is between 0 and 1, which proves that our solution is between 1 and 2. So I think this is these are some really cool problems. Alright, so here we have a similar problem involving a quadratic equation, and we have to prove that x squared equals 2x plus 1. We have to prove that the solution is between 2 and 3. This is going to require more steps, but it's not that bad. Okay, let's put everything on one side. So we got x squared minus 2x minus 1 being equal to 0, okay? This looks a lot like x minus 1 squared. If that was a plus 1, it would be an x minus 1 squared. So what we're going to do is we're going to take x squared minus 2x, and then we're going to plus 1, and then we're going to subtract that 1, okay? And then we're going to subtract this 1, okay? So all I did here is I added 1 and subtracted it immediately, okay? And then we're going to set all that equal to 0. So why did I do that? That is so that we can do this. X minus 1 squared, okay? Minus 2 is equal to 0. So this stuff goes there, and then this stuff goes right there, okay? From this, we can actually subtract 2 on both sides, or I'm sorry, add 2, and so that is equal to 2. And then x minus 1 is equal to the square root of 2, but in this case, it has to be plus or minus, because we're not done yet, because we still have to add the 1 on both sides, and that just means we're not really done yet, so I'm going to keep the plus or minus just for safety, okay? So now we have two cases. We have a case where x is 1 plus square root of 2, and a case where x is 1 minus square root of 2. We can do both, but we only need to do 1, because that will prove this for us. So I'm only going to do 1. If you want, you can do the minus, because I'm going to do the positive 1. But if you want, you can do the minus, and that'll give you some practice, okay? So here we have to prove that 1 plus square root of 2 is between 2 and 3. So 1 plus square root of 2 is between 2 and 3, okay? Is square root of 2, okay, if we subtract 1 from all the sides, all 3, we can isolate square root of 2. So this is 1 square root of 2 and 2. This is valid. We can do this, okay? But what do we do now? Well, this is what we did in the first problem. We set this equal to, this is a square root of 1. Square root of 1 is 1, okay? This is square root of 2, and this is square root of 4. Okay, is square root of 2 between square root of 1 and square root of 4? Well, again, we can do 1, 2, and 4, and we can see that it is. It is between these two boundaries, and therefore, that there is a solution between 2 and 3. So now if you want, you can do the case where 1 minus square root of 2 is between 2 and 3. Alright, so now we're given the equation e to the x is equal to negative x. And first we're going to prove that there is only one solution. Now you could do this through algebra, but I think the easiest way to do that is by graphing it, okay? Because these are functions that we can predict where they're going to go, okay? So I'm going to just draw a little graph for myself there. Okay, so I'm going to draw e to the x in purple, okay? So e to the x goes like that, okay? It doesn't touch 0, but it gets really close, so we're going to leave it, okay? And then, so this is e to the x. And then I'm going to do negative x in blue. So this is going to go like that. That's good enough. And that, okay, that's good enough. That's a straight line. And so all we need to do is just show that, okay, this is going to keep going that way, and this is going to keep going that way and that way, so they're never going to intersect again. If you can explain that, you've proved it, okay? So that's it. We proved it. There's only one solution. It's never going to touch again. It can't, you know? So now we're going to prove that that solution is between -1 and 0. Well, it's obviously less than 0. Like, we see that right there, because this is 0. But is it greater than -1? Let's assume that it is, and we're going to draw a line like here. Okay? Drew that a little close, but it's still there. Okay. So what can we do? We don't have anything to plug in because we didn't solve for anything. We just graphed it. But we can draw a little table here. So let's get our values. We have x, e to the x, and negative x. Okay, e to the x and negative x. So then I can just do that. And we only need two values. We need -1 and 0. And you'll see why, but that's what these are, okay? So e to the -1 is just 1 over e. So it's it's about 1 over 2, 1 over 3, somewhere between there, because e is 2.71828. But okay, so negative of negative x is just going to be 1. Because, or I'm sorry, negative of negative 1 is just 1. Okay. So then for our 0 value, e to the 0 is 1, but negative 0 is 0. This is all we need. We can now use our graph to help us out. So when x is negative 1, e to the x is going to be 1 over e. So this point right here where the purple line intersects the orange is 1 over e. So I'm going to try to make that clear there. Yeah, 1 over e. Okay. But when x is negative 1, the blue line is going to be 1, which makes sense because it, so then this here is 1. So where this blue line touches, that's 1. Okay, this is confusing here. This is 1 over e, and this is 1. Okay, hopefully that's not confusing. Now, when x is 0, e to the x is 1. So our purple line is 1. It actually conveniently is there. Okay, so that's good. That's 1. And then when x is 0, negative x is 0, which makes sense too. So it's right there. That's 0. Okay. So we have all our values, and what does this tell us? Well, it tells us that what we drew is accurate. We proved that what we drew is how it is, and that all these points are valid, and they are where they're supposed to be. Therefore, since our graph is accurate, we know that it does intersect. And so because if we proved through here that our graph was inaccurate and that we drew it wrong and that it doesn't actually intersect there, then they wouldn't be between this region. But we did. We showed that they do intersect in that region, and therefore there's a solution there. So hopefully that wasn't too confusing. But yeah, that's there are different ways. You should always look for different ways. Solving an equation isn't always the way to find a solution. Sometimes the easiest way is to graph. So yeah, thanks for watching, and I will see you in the next episode. Bye.